So let's recall a few things. If you have a function of two variables, say, so this is a graph of your function, and this is your y-axis, x-axis, and you would like to find the partial derivative with respect to x. So that means you're looking for the derivative at a point, say AB, but that derivative is in the direction of the x-axis. So you'll be looking at the tangent line along this direction, right? And then you can also say, okay, I want to find the partial derivative with respect to y. That would be the derivative along the y-axis, in the direction of your y-axis, something like this. So you'll be looking for the slope of the tangent line, in that direction. Now, so it's either this direction, or that vector as a direction, or this vector as a direction. Okay. Now, how about if we want the direction to be any ordinary direction, like this direction? What's wrong with that? What's wrong with this one? And so forth, right? Okay. So, in other words, let's try to make this in, let's try to do it in 2D. Let's try to explain it better in 2D. So you have your x-axis, then you have your y-axis, right? So partial derivative your partial derivative f of x takes this direction, right? It takes the direction of that vector. This vector is 1, 0. 1, 0. And then the partial derivative along the y-axis takes this direction, right? Partial derivative with respect to y, fy, and this vector is 0, 1. Now, how about if we just want the direction of any unit vector? Say we have this unit vector right here, or this unit vector, right? Which would be parallel to any unit vector at all. Let's say we have which could be parallel to any unit vector, say this unit vector, right? Or this vector, it doesn't have to be unique. Let's make it that. But let's focus on the pink one, the pink vector. Right. Or you know what? Maybe we shouldn't. Let us see. Okay, I know what to do. Yeah, I know what to do. So this is a unit vector. And if this angle is, say, theta, okay, then if you try to complete the right angle triangle, this part of this right angle triangle would be h cosine theta, and this part would be h sine theta. That means that this unit vector is now the vector, let's call it u. So u now is going to be the vector, let's call it u1, u2, just going to be the vector h cosine theta and h sine theta. But assuming if the vector is unit, if the vector is a unit vector, that means its length h is just 1, because this is u, but this, let's call this length h. That's why I said h sine theta and h cosine theta, right? So, but if h is 1, then we just have this as cosine theta and then sine theta. Okay. I hope that makes sense. I think it does. All right. So all we want to do is we want to find the rate of change of a function. We would like to want the rate of change along any unit vector u equals u1, u2. All right, so this is our function z equals f of xy, and we want to find its rate of change along any unit vector u. So this could be u, it could be this one. All right, now that brings us to the concept of the directional derivative. So we can now define what a directional derivative is. If we let f be differentiable at the point xy, and if we let u be any unit vector, cosine theta, sine theta, right? Let it be any unit vector, because any unit vector can be parameterized as as cosine theta, sine theta, just like we explained here. And because if it's unit, then this length, its magnitude, which we're calling h here, is going to be equal to 1. All right, so in that case, let it be any unit vector in the xy plane. The directional derivative of f at xy in the direction of u. Call it u, in the direction of u. Well, we might as well put the arrow whenever we can remember it. In the direction of u is defined as, its notation is d u f xy. It's the limit as h goes to 0 of f of x plus h cosine theta y plus h sine theta minus f of xy all over h. Okay, all right. As you know, anything that comes with limit in calculus, any definition of a derivative that has limit in it, can be challenging to compute for any kind of arbitrary function. So there are usually theorems that are developed to handle definitions that have limit in them. I'm going to explain one of those theorems, but before that, let's look at the concept of the gradient. If we let f be a differentiable function at any point xy, just like we written before, let f be differentiable at any point, at a point xy. Then the gradient of f at xy is the vector valued function. The vector valued function fx at xy, fy, xy. So the gradient is simply a vector that has two components, or it could be three components if it's a function of three variables. But in our own case, we're looking at functions of two variables. It's a vector whose first component is a partial derivative with respect to x, and the second component is a partial with respect to y. All right. Now, this is the theorem that is going to make it easier for us to compute the directional derivative. So the theorem, its assumption is that f is differentiable at x and xy, and u is a unit vector in the xy plane. All right. So f is differentiable at xy, and u equals u1, u2 is a unit vector on the xy plane. All right, this is very important. It has to be a unit vector. If that's the case, then the directional derivative is the gradient dot u. Okay, so it's the gradient at xy dot u. We know how to compute the gradient. All right, so this is the only method of computing the directional derivative that we're going to use in this lecture. So let's look at some examples. First example, let f of x, y, be 2x squared plus 5xy minus y cubed. The first part, find the gradient of f. The gradient of f is that, and it is the vector whose first component is the partial derivative with respect to x, which is 4x plus 5y, and then its second component is the partial derivative with respect to y, 5x minus 3y squared. And then we want to find its gradient at 1, 2. So it just means plug in 1 and plug in 2 in the gradient. That's all. It can be very simple sometimes. Plug in 1 and 2. So if that's the case, plug in 1 and 2. When you plug in 1, yeah, I see 14 and I see negative 7. I think I'm right. Yeah. Okay. Let's try one more problem, and then we can try other things too. So if we let f of xy be equal to 3 minus x squared over 10 plus xy squared over 10. 1, or A part, we want to compute the gradient at 3, negative 1. So the gradient at xy, any random xy, is x over 5, no, negative x over 5, and then 2x over 5 over 10, which is just 2xy over 10, which is xy over 5. xy over 5. So that's what we have. And then this tells us that the gradient at 3, negative 1 is going to be, plug in 3 there, you have negative 3 over 5. And then plug in 1, you have, plug in 1 and 3, you have negative 3 over 5. I think that's what we have. Okay. Now, how about we compute the directional derivative, derivative of f at 3, negative 1 in the direction of the unit vector 1 over square root of 2, 1 over square root of 2. All right, so I have to warn you, if you are not given a unit vector, then you have to make the vector a unit vector first before you compute the directional derivative. So that's our directional derivative at 3, negative 1. It's just going to be the gradient at 3, negative 1, dot our u, the directional, the unit vector 1 over square root of 2. So the gradient at 3, negative 1 is negative 3 over 5, negative 3 over 5, then dot 1 over root 2, 1 over root 2. Something tells me I'm doing something wrong. I don't know. Sometimes I get that feeling, that bad feeling. Okay. I think I'm not yet. All right, so this is negative 3 over 5 square root of 2, then minus 3 over 5 square root of 2, which is negative 6 over 5 square root of 2. That's a weird answer, but sometimes some answers are weird. All right, so I want you to try this one. Remember what I just warned you about. So I want you to compute the directional derivative of f at 3, 1 in the direction of the vector 3, 4. All right, now there are a few other things we can do. So assuming you have a function, a 3D function. Let's look at our 3D function as this elliptic paraboloid. So a 3D function, think of this function No. Okay. And you are somewhere here. You are at this point. And this point is, say, A. Its x coordinate is A. Its y coordinate is B. And its z coordinate is f of AB. All right? And you want to keep climbing along this paraboloid. You want to go up. Sometimes you might want to go down. All right? We like to ask the question of, what direction do you take? What direction would make you climb along this surface the fastest? And that direction, let's project that direction on the xy plane. So is it this direction? What direction is it going to be to climb fastest? Or, so if you're climbing, if we're walking along, assuming you're projecting what you're doing, you're moving along the surface, but you're projecting it on the xy plane. Remember, this is your y-axis and this is your x-axis. What direction do you go on the xy plane to move the fastest along the surface? That's the question. And we can answer that question with a theorem, which I'm going to write now. This theorem is very loaded. It's loaded. All right. Let f be differentiable. Differentiability is very, very important. So that just means we can find the derivative. The derivative is not undefined, or there is no kink or squeeze at that point. All right, so it's differentiable at the point AB with the gradient at AB not equal to the zero vector. It's not equal to the zero vector. Now, f has the maximum rate of increase. Maximum rate of increase. Increase at AB is the gradient. The maximum rate of increase, is in the direction of the gradient. And the maximum rate of increase is actually the magnitude of the gradient. And if that is the case, that means that the maximum rate of decrease is in the direction of negative the gradient. And the maximum rate of increase or maximum rate of decrease is negative magnitude of the gradient. And then the direction of zero derivative. Well, let's put it this way. Let's write it this way. The directional derivative is 0 in any direction orthogonal to the gradient. This is 3, not B. All right. Remember, the directional derivative is the rate of change along a direction. So the direction that will give you the maximum rate of change is the direction of the gradient. The direction that will give you the maximum rate of decrease is the direction of negative the gradient. Direction of maximum rate of increase is the direction of the gradient, right? And the direction of no increase is any direction orthogonal to the gradient. Now, I am going to assign a question, and we can see how this works. So I'm going to change this to Roman numerals. So that I can call my next example, example 3. Example 3. So let's consider a bowl-shaped paraboloid. And this bowl-shaped paraboloid is z equals f of xy is equal to 4 plus x squared plus 3y squared. Okay? And then let's assume we are, so the bowl-shaped paraboloid, just like the paraboloid I had here, I'm just going to copy this instead of trying to draw it again. I have this here. So, and we would like to compute the maximum rate of the maximum ascent rate and the maximum descent rate. So, and the point we're looking at is 2, negative 1/2, and 35/4. Okay. So let's consider the point 2, negative 1/2, 35/4. Okay. I want us to compute the maximum rate of increase and the maximum rate of decrease if we are on this point, right? And we want to climb up, what direction do we take? If we want to climb up the fastest, and if we want to go down the fastest, what direction do we take? That's all we're going to compute. But to do that, we have to compute the gradient. We have to compute the gradient. So we find the gradient. The gradient of our function is is 2x, right? And then 6y, I think. So if we compute the gradient at 2, negative 1/2, we're just going to end up with 4, negative 3, I think. Right. Okay. So our direction of maximum increase, we also call this steepest ascent, direction of steepest ascent, is just this direction, 4, negative 3. And rate of steepest ascent is just the magnitude of that vector. It's just magnitude of 4, negative 3, which is the square root of square root of 4 squared, right? Plus negative 3 squared, which is, I think this is gonna be 16 plus 9. This is just 5. So that means that the direction of maximum decrease, which is steepest descent, is gonna be negative 4, negative 3, which is negative 4, 3, right? Rate of steepest descent is negative 5 now, all right? Because it is negative magnitude of 4, negative 3, so it's just going to be negative 5. Okay. Direction of no change. Direction of no change. Choose any vector that is orthogonal to 4, 3. So we want a vector that when we find the dot product of that vector with 4, negative 3, we end up with 0. So what two vectors do we dot to get 0? Think about it. We want to get 0. The easiest vector would be a vector that has maybe 3 here and negative 4. Let me do it in green. How about 3 and negative 4? It's not magic. You just want 4 times 3 plus negative 3 times no. I'm gonna switch it. Switch it. I'm gonna put negative 3 here, and then I'm gonna leave that as 4. So I'm gonna do 4 times negative 3 plus 3 . No, I'm very sorry. I think I'm messing something up. I just want to get 0. I'm overthinking it. That's what's happening. All right. I know. I was right the first time. I was right. So I'm going to put 3 here. All right. I have 4, negative 3. Just leave it at 4 and 3. I just want to get 0. So I have 4 times 3. And then times 4. All right, so we have 4 times 3 plus negative 3 times 4. This will give us 0, right? So you just want two vectors that when you multiply them, you get 0. So in general, how to do this, if you have AB, if you dot it with B, negative A, you're always gonna get 0. So whatever you have, just flip it and put a negative on one of them, right? You get 0. Okay, so when I say put a negative on one of them, I just mean put a negative on one of the components. If it's a negative, change it to positive, something like that. We're going to talk more about this in class. I'm going to stop here. I will see you in class. Or